Okay, welcome everybody to our second week of 5th Geometry-Topology Summer School of Nesin Mathematical Village. So this week we're going to have lectures of Özgür Kelekçi on Einstein-Maxwell manifolds. So he's going to introduce lots of introductory material, some tensor calculations done very efficiently. So I hope you're going to enjoy it very much. So very central material, and at the end he's going to talk about Einstein-Maxwell manifolds as well. So let me leave you with him now. Thank you very much.
Okay. Okay, thanks for the introduction. So we will start with Einstein Spaces. So how do we obtain these spaces? Especially we need to look at Einstein field equations. I can zoom in a little bit. So let's start with Einstein field equations. I'm giving these long definitions. Actually, then you will be able to read on your own, but to be self-consistent, I'm giving these long definitions. So the fields such as the electromagnetic field describe the metric content of space-time. Here, M is a connected four-dimensional manifold and G is a Lorentzian metric. And these fields obey equations which can be expressed as relations between tensors on manifold in which all derivatives with respect to position are covariant derivatives with respect to the symmetric connection defined by the metric G. The equations governing the matter fields are such that there exists a symmetric tensor T mu. We will go into details of it later. Called the energy momentum tensor, such that the relation between the metric field G mu and the material contents of space-time is expressed by Einstein field equation, as we show in this neat equation. We are going to give the meanings of these tensors shortly. But if we first have a general look at this equation, the left-hand side is related with geometry of the space-time or the manifold, and right-hand side is the matter content, energy, mass, and related stuff. By the way, we use Ricci calculus notation, where you feed the metric with these vectors. We write with this index notation. Here, lambda is cosmological constant, R mu the contracted curvature tensor, as you may remember. It is obtained from Riemann tensor, the contraction of the first and third indices. This is the Riemann tensor. And R is its trace, G mu. R is the scalar curvature. And kappa is a constant linked with the gravitational Newton's constant. The energy momentum symmetric tensor depends on the fields, their covariant derivatives, and the metric. These fields are matter fields. So if we turn back to our subject, which is Einstein-Maxwell manifolds, it comes from actually they are solutions to Einstein-Maxwell equations. Here we have cosmological constant lambda set to 0. And by the way, if you experience any problem, voice or image, please let me know. Okay, we set cosmological constant to 0, but we keep stress energy momentum, stress energy tensor of the electromagnetic field on the right hand side. Generally, we call this part I mu nu minus 1/2 G mu nu R as the Einstein tensor. I menu is the Ricci curvature tensor, R is the scalar curvature tensor, and G menu is the metric tensor, and T menu, as we just said, it is stress energy tensor. At the beginning, these are very basic. I guess most probably you all know parts of this lecture. Anyway, so if we start with the definition, first we want to obtain these Einstein field equations by starting from Hilbert-Einstein action or functional. So the MG be a compact-oriented pseudo or normal Riemannian manifold, and DVG is the volume element given in coordinates, as given DVG equals square root of determinant of G times the top form of the manifold. The following functions are defined for this manifold. Volume defined by G is given by this equation, and Hilbert-Einstein action or function is given by this integral equation. R is the scalar curvature function of the metric. It is defined from the manifold to the reals. And as we said, this also called total scalar curvature. This action can be also called total scalar curvature of the manifold. And as a special case, when the dimension is when dimension equals to 2, then this action becomes this integral equation. Here, this comes from Gauss-Bonnet theorem, and as you remember, K is 2K is R for dimension 2. K is Gauss curvature. 4 pi chi of n. Chi here is the Euler characteristic. This is just to mention a special case. We don't have any special focus on this two-dimensional case. Okay, so we need to apply variation to this Hilbert-Einstein functional in order to obtain Einstein field equations. Just to remind you the basic of variation, I am giving this simple definition. If we have a manifold M with metric G, the variation of the metric in the direction H with the real parameter T is defined by this equation. Here, H is an arbitrary but fixed symmetric 0-2 tensor field, and the derivative of the real valued function T to S of GT at the point T equals 0 can be viewed as a direction derivative of S in the direction H at the point G, and we can study the variation problem. Delta SG equals 0, and here is how we apply the variation. I'm giving this just to remember that variation is acting like a derivative, so we use the properties of derivative. So we vary the metric arbitrarily, where the variation should vanish at the boundary of the integration domain, including infinity. So we take our metric G mu nu goes to G mu nu plus delta G mu nu, and at the boundaries, this delta G mu nu goes to 0. And here we use the action principle. In order to derive dynamical equations for a physical system, we use the principle of least action. It means that the action remains stationary with respect to small variations of a field, like here. And this view provides the important bridge between symmetry and conservation law. This is an important principle in physics, and we use it here. So let's write the action as we have given here in this definition. Square root of G, scalar curvature R, and this is dx1 range up to dxn. So here, by action principle, delta S has to be 0. So we apply delta variation to the integrand of this integral. Here we have square root of determinant of G times scalar curvature, and we apply the variation. As we said, it is applied like derivative. So R, we can write R as the product of inverse metric with the contracted indices of Ricci scalars, Ricci curvature tensor. So we just need to apply variations to all three terms. So the first term becomes delta of square root of G times G mu nu R mu nu, which is just R. And the second, we apply this G mu nu, and the third one should be applied to standard derivation. Here we are going to also use the metric compatibility. This is metric compatibility, as you remember. And here we are going to use Palatini identity. Actually, it is a simple identity which gives us the variation of Ricci tensor. And as a hint, actually it's a straightforward calculation. So I'm giving you this as an exercise. You just need to write R mu as alpha nu, and apply delta to both sides, and write the Riemann tensor in terms of its definition, which includes Christoffel symbols. Then you are going to end up with this identity. It is straightforward. So we are going to use that here. So let's multiply this star equation with metric and square root of G, and that gives us, let's see, square root of G times G mu nu inverse metric. As we have the metric compatibility, it goes directly inside of the covariant derivative here also. Please try to follow the steps and ask if you have any questions. So here, let's see, G mu nu, since nu is summed over, here also I need to mention we are using Einstein summation convention, meaning if you have an up and down index, say I, if you see this one up and down, same indices, then it's automatically summed over I up to the dimension of the manifold. So that's something you need to consider in all repeated indices. Okay, so here nu is summed over, so I can change it to any other index. Here I can change alpha to rho. It's also summed over. So if you make this in exchange, in order to obtain covariant derivative alpha and to get under the same covariant derivative, we end up with this tensor. This is tensor because we have a we have the difference of Christoffel symbols, so this we can show as V alpha. And so what we have here is covariant derivative alpha V alpha, and by definition of covariant derivative, and if you open it, you'll obtain this as a total derivative. So this becomes a total derivative. When you open this, you'll end up with this. What we have here, normally it is under, it's an integrand. We have an integral here over the manifold. So this is a total derivative, as we have just found out. Then we can use Stokes' theorem here. Remember, if you have a form, one form like this, and it is calculated on the boundary with omega, and this term yields only a boundary term here. This part, normally you have partial derivative, but since we have taking the integral, we end up with this part. And it yields only a boundary term when integrated, so this will not contribute to the action where delta G mu nu goes to 0, and also derivative of G mu nu, variation of derivative of G mu nu goes to 0 at the boundary. We need these two. At the beginning, I guess we just mentioned this, but we need to also postulate this one because we have Christoffel symbols, and in here we have G mu nu metric and the derivative, partial derivatives of metric. Actually, this is also has to be, it has to be physically. It is called Einstein, Gibbon, Hawking, York boundary term, I guess. So then this term, this third term goes to 0 because it's a boundary term and it goes to 0. So we are left with two terms. So now let's compute the first term of equation 1. We need delta variation of square root of G, and as I said, it applies like derivative, so we just take this derivative part, 1/2 square root of G delta G. So we need the variation of G determinant, and determinant of G mu nu is, we know this identity, exponential trace ln G mu nu. So if then we can write this equation, ln G is equal to trace, and you see this. And if you now we apply variation to both sides, here we are going to obtain delta G over G, and here trace G mu nu delta G mu nu. Then we obtain here, follow this, delta G is equal to G times G mu nu delta G mu nu. This is also already traced. Then let's use this in this part here. So if you use that in here, it becomes 1/2 square root of G, and so this cancels 1 square root of this one, and we have 1/2 square root of G mu nu delta G mu nu. Then we can apply this to the first term. This was already R, the Ricci scalar or scalar curvature. Then we end up with this part. Now concentrate on the second term of this variation. Let's see, this one. So here we just need to obtain a variation of the inverse metric. In order to do that, let's remember that G mu inverse metric times the metric will give us Kronecker delta, delta mu lambda. And if we apply variation to both sides, since this is a constant 1 or 0, variation of it is 0. And for the left-hand side, first you apply the inverse metric and then you apply to the metric. So this yields delta G mu inverse metric is becomes equal to this part. We again applied some index change in order to not to confuse some of the repeated indices. Then then we also have, when we look at the term, we have delta G mu R mu. We already obtained this variation, so then just multiply this R mu. So minus G mu sigma delta G sigma lambda G lambda nu here, and we have two inverse metric components here, two inverse metrics. Then they just raise the indices of this R mu nu to up. And then since these are again summed over, these are dummy indices, so I can change them back to mu nu. So delta G mu R mu becomes minus delta G mu R upper index R mu. But let's also not forget square root of G. So finally we have two, the third term was shown to be 0. Then we are left with two terms, and we have delta G mu and square root of G in both terms. One term is this one we just obtained, minus R mu square root of G and delta G mu, and the other one was already obtained, 1/2 G mu R square root of G and delta G mu. So from the action principle, delta S has to be equal to 0. Then we obtain the Einstein equation without matter. Here, this has to be 0. I just take the negative of this because it's already 0. And this is by definition called Einstein Tensor. Is R mu, and by just lowering the indices, you can also write with the index down. But here we just obtain the without cosmological constant and without matter fields. Now, if you also include matter fields in the action and also the cosmological constant, what will happen? Here, matter fields, we mean you have a scalar phi, it's a covariant derivative, and the metric, it depends on all these terms. Again, this is a Lagrangian, and this is the action for the matter fields. So for the total action, which includes the Ricci scalar, the cosmological constant, and the matter part. We can write them in one action like this. Then again, we are going to apply the variation to this part altogether. Here we have 2 kappa, as we have mentioned. It is just a constant. The first part we already obtained, square root of g, delta g mu is here. This part is obtained. And let's focus on the second term, the term with cosmological constant, and apply the variation. Since lambda is already constant, we just have delta variation of square root of g, and we obtained this in the previous steps, and that is 1/2 square root of g mu delta g mu. So if we put it here, g mu is here, inverse metric square root of g, and delta g mu is here, and we I'm just multiplying everything with 2 kappa here in order to get rid of this part. It's just a constant. So when I multiply this by 2 kappa, this is cancelled and kappa cancels, and since I have 1/2, 2 also cancels. So I'm just left with this, and g square root of g and delta g mu is there. And the third term, the matter part, let's times Lm. So since we have two terms here, the first one we will apply on as again delta of square root of g times Lm, and this term square root of g times delta Lm. And delta square root of g, as we obtained before, it is here, and times just Lm, so it's here. And the second one, let's see, it's just delta Lm and square root of g, and I just need to divide by delta g mu, and so it is here. And since I multiply by 2 kappa, it is here. Good. Here at this point, we are defining the tensor T mu with the up in indices, and it is g mu Lm, just this one, just this term, g mu Lm plus 2 del variation of Lm over variation of g mu. Then if I define this tensor and put it here, insert here, then this has to be altogether 0. Then what we get the equation r mu minus 1/2 g mu r. I'm just again multiplying by a negative sign, and lambda g mu, and if I take this to the other side, kappa t mu. And this is the full Einstein field equation, and we obtained this from the variation of the action. Okay, up to this point, if are there any questions? I guess I hope you could follow these calculation steps. Okay, so let's continue with another definition. A Riemannian manifold MG is called an Einstein space if the Ricci tensor is a multiple of the metric G. This is the very basic definition of Einstein manifolds or space. And Ricci takes tensor as a xy as entries and lambda gxy. Or in index notation, you can write r mu is equal to lambda times g mu. And this is valid for all x and y, and the constant lambda real constant. So Einstein manifolds are solutions of Einstein's field equations for pure gravity or vacuum solutions. We call when we take the right-hand side of this general Einstein field equation. If we set the right-hand side to 0, we call this vacuum solutions. That means there's no mass or energy in the system. But we have a cosmological constant. So we can check this. So this is the vacuum solution, vacuum Einstein solution equation, and we are looking for solutions. So let's apply inverse metric to both sides, G mu nu. So this becomes scalar curvature, and G, if you contract inverse and normal metric with itself, this becomes delta mu nu, and this will give you the dimension of the manifold. You can see this. This is a general identity. So here we obtained 1/2 n times r, and also here n. And from here, r, if you take the r parentheses, then take these to the other side, and you obtain r equals lambda cosmological constant times 2n over n minus 2. And then insert this into the first equation here. Instead of scalar curvature r, we are going to use this equality. R mu nu minus 1/2 G mu nu lambda. Instead of r, we put this, and lambda G mu nu here in this equation. Then what we get, r mu nu, and if you take the parentheses, common parentheses for lambda G mu nu, you obtain this. And then, okay, so this is the relation between Ricci tensor and the metric tensor, 2 lambda over n minus 2. And according to our definition, we have a small lambda, and that is just 2 capital lambda over n minus 2. Gaussian curvature, and it's a scalar function defined on manifold to reals. Then there's a single curvature tensor for 2-dimensional manifold. R is equal to k times R1. This is already known. And so that means it satisfies the definition of Einstein space. And any manifold with constant sectional curvature, here, for example, if this is constant, then according to our definition, R becomes some constant lambda times G mu nu. In this case, it becomes just R1. Constant sectional curvature is an Einstein manifold. For example, take Euclidean space, it is flat, and it's a simple example of Ricci flat Einstein metric. In this case, R and K equals to 0. Maybe to make it bigger. An n-sphere with the round metric, it's also Einstein. R equals R1. here, according to this, k equals to 1 and lambda is n minus 1. Hyperbolic space Hn is also Einstein. Here r becomes minus r1 and k is minus 1 and lambda is equal to minus n minus 1. Complex projective space CPN with Fubini study metric and lambda is n plus 1. And we also have Calabi-Yau manifolds. These are very special manifolds and they admit Einstein metric that is also scalar and they are also Ricci flat. So these are the well-known examples of Einstein spaces. Now also give this definition and the theorem. The Einstein Tensor G, as we have given before, is defined as G Ricci tensor minus here S is actually R according to our notation. R meaning this is scalar curvature minus S over 2 times G meaning. On an arbitrary manifold, the divergence of the Einstein tensor vanishes. So that means divergence of Ricci tensor becomes, when you apply div G equal to 0, then the divergence of Ricci is equal to, has to be equal to divergence of S over 2 times G. Or in Ricci calculus notation, we can write this with this equation. Covariant derivative I, J, K, you can raise the indexes up and down. Here, G, J, K is just R, J, K minus S over 2 G, J, K. We are going to prove this, but before that, let's give an lemma. For every x, we have this equation, trace of covariant derivative with respect to x of Ricci tensor is equal to 2 times divergence of Ricci evaluated at x. Or in Ricci calculus notation or index notation, we can write this 1/2 covariant derivative L of R. I take this to the other side, so and this is contracted with this index. So let's prove this. We need the second Bianchi identity. So from now on, I need to write notes real time. I hope we don't have much delay. Here we call second Bianchi identity. Which was covariant derivative I applied on the Riemann curvature tensor LJK. You just shuffle the indices J, M stays there, other indices are shuffled, K, M, Lij equals to 0. So this is the second Bianchi identity. And let's apply inverse metric and metric. Apply here. So let's see, G, Aj. Since we have the metric compatibility, it just the covariant derivative operator is transparent to the metric. You can just go inside of the covariant derivative due to metric compatibility, so that lowers this M index, JK, J, just lower the M indices in all derivatives, covariant derivatives, RJK, RA, and RG to 0. Then also apply this inverse metric. I. Then what happens? It now it, what does it do? It raises this A index back to here. But then we have J and JK. And here it also applies to index of the covariant derivative. So that gives us A and Ki plus let's just use the property of the Riemann tensor, which is antisymmetric in the last two indices. This is K, Rj. Later it will be known why I'm doing this, and Ji, because there is this contraction in first and third indices that will give me a Ricci tensor. And I just swap these two indices and take a minus sign here. Lj I, and that is equal to 0. Okay, let's write and also apply another inverse metric I. So here J and J, so we have R, L, K. This is the Ricci tensor. Here, let's also use the property of the last two indices. It's A, R, A. So, no, here, not the last two indices, but the first two indices. L, A, K, I. If you see any typo, please just inform me about it. I can't check this, but in any case, equal 0. I didn't do anything, just write this by definition. And here I just change the first and second index. And let's apply another inverse metric here. So that gives us, let's see, I, R, the first term. And let's take this to the other side of the equation. A, it's RK. Since I applying LK, so this goes up. K, A, K, I plus L, R, and I, and that is equal to this one again, first and third indices. So it is Ricci tensor by definition. And I. Okay. So the last step is just to write everything in one equation is equal to, since these A's are summed over and L are summed over, I can write them together. So I have here 2 L R and I, because these L and A are summed over, so they are dummy indices, and I can change them. L R L I. So that's what we claimed in the lemma. Let's see. Now let's go to the proof of theorem 1. So we start with this K, JK, just using this lemma. Vector lemma 1. We take the covariant derivative of Einstein Tensor, djk, which is k rjk minus k scalar curvature. I am using R for that. Gjk So this, if I apply this covariant derivative to this product, scalar curvature times the metric, what I'm going to obtain is k gjk plus gjk number k r. We know this is 0 due to metric compatibility. And so we can also raise and lower index of the covariant derivative, so that becomes JR. And then let's see, K JK is K R JK minus K R over 2 GJK, and that's equal to K RGK minus 1/2 J, we just obtained that, J R equal to 0. Let's see. So it's here. We obtained that one. I just can copy this to here. And let's compare with our obtained results. Yes, LR M RML. So it's the same. We got RJK. So that means the Einstein tensor is divergence-free, divergence-less. According to this theorem, we just proved. Here, according to here. Okay, let's give another theorem. And after this theorem, I think I'm gonna stop for today. Theorem. Let MG be a connected Einstein space of dimension and greater or equal to 3 with actually Einstein space already include that, but just let's mention that. Then lambda is constant and if n equals 3, then MG is even a space of constant curvature. Even a space of constant curvature. And proof for that, we have this divergence equation, divergence of Ricci is equal to divergence. And so 2G, and inserting for the Ricci tensor, inserting Ricci tensor, which is lambda G, and taking the trace, if you take trace of left-hand side, it is scalar curvature, S or R, and if I take the trace of this, it will give me the dimension of the manifold N, and there's lambda. Then apply this in this divergence equation. Lambda G. Here, instead of Ricci, I'm using lambda G by definition. And here we have n lambda over 2 G of X. So we have n over 2 divergence lambda G type of X. And since we have metric compatibility, is 0. The left-hand side can be written as so we get X lambda here. EIs are the elements of the orthonormal basis. N over 2 X lambda. From that equation, for arbitrary X, which implies that either n equal 2, n equals 2, when you just insert n equals 2, then this is satisfied, or X lambda has to be 0 for all X, provided n greater or equal to greater than or equal to 3. Thus, for n greater than or equal to 3, lambda function is locally constant, and since M is assumed to be connected, it is also even globally constant. That is understood. I guess in case n equals 3, the Ricci tensor alone determines the sectional curvature. And let's take an orthonormal basis. An orthonormal basis, which is E1, E2, E3. Then R11 is just E1, E1, and by definition that is equal to K12 plus K13. And for R22, it is K12 plus K23, and R33 is K13 plus K23. Okay, the last thing that we are going to mention, if the left-hand side of three equations if the left-hand side of these three equations are each equal to lambda, equal to lambda, then what do you obtain? We obtain K12 is equal to K13, and that's equal to K23, and that is lambda over 2. Since this holds, in an arbitrary orthonormal basis, an arbitrary orthonormal, it's a well-known abbreviation, I think, basis, the sectional curvature is constant. The sectional that's, I think, what we stated in the theorem. For n equals 3, we have constant curvature. Okay, I think, let me check. For today, this is the introductory part that I wanted to give. Then we will go on with conformal transformation and some classifications and so on. Okay, I think I will stop at this point. If you can please give me some feedback if it's too fast, too slow, too simple, things like that, then I can arrange my notes later. So if you want to, recap, we started from the scratch of the Einstein-Hilbert action or functional, and we applied the variation and obtained the most general Einstein field equations, which is an important part. And then we give some examples and some important theorems, which may be later useful.
Okay, thank you very much.
Any questions?
Okay, so it's a good point to stop. So thank you very much, Özgür, for this nice lecture. And we're gonna start, restart at 2:30 in the afternoon.